So, welcome once again. We are taking gradual steps to come into the main themes of calculus. Today we are speaking about limits. Now, many of you, the more ambitious younger students, possibly waiting urgently to get some knowledge about limits, about derivatives, integrals and all those things. I would suggest that you would keep this in mind, that you would understand calculus far better if you know at the very outset that these derivatives and integrals are names given to some special kind of limits. So, limit is actually the most central and possibly sometimes viewed as a very slightly difficult concept in calculus, and you will understand calculus much better if you know at the very outset that every continuous function did not have a derivative. We will come to all those things later, but first of all let me tell you what is calculus actually, what does calculus study? It is just to write some derivative something from the air and then you just get some marks in the examination? Is that for the reason for which you study calculus? Of course, many of you would say, okay, I have to do it in my IIT JEE, I have to give my engineering exam math 1 course, so I will just do something, I have to know the tools, I have to apply it, blah blah stuff. But the real issue, which is hardly seldom told in our class, is that calculus studies change. It tells you that if I have a function written in this form y equal to f of x, then what happens to how does y changes when x changes? How does the function value change with the change of the independent variable, the x variable which we call the independent variable and this the dependent variable. Calculus actually deals with the rate of change per unit time. So, time also gets linked with calculus. This variable largely has been talking about time. So, calculus arose because people wanted to understand motion, and if you read if you look at the history of calculus, it was essentially while trying to understand motion of bodies, motion of heavenly bodies rather, that calculus first took its root. And it first came in when people started talking about the velocity of object at a given time, instant. So, what people like Newton and others realized that if I want to look at the velocity, how a particle is moving, I can draw a graph and I can put this x t as a function of t as the position, because you can understand that you can always consider time when you are standing still at time t equal to 0, then you start moving. So, as you move the distance changes, but as time flows you cover more distance. For example, a train starts at 3 o'clock from the Howrah station and has to go towards say the Bandel station. So, then for example, it starts moving at 3:15 it is at the next station Lilua, and 3:30 it is at some other place, 3:40 it is at some other place, and so on and so forth. So, distance is essentially a function of time. So, the graph could be straight like this or graph could be something like this. So, even at discrete times you can do like this, you can plot it like this. If you observe it say after 30 minutes time interval, assuming that time are given minutes or even seconds. So, at every 60-second interval. So, it could be like that. So, as the train starts its speed increases and you see the speed is increasing, and so you basically have some sort of an increasing function if you look at in continuous time. So, now the question is what was its velocity at 3:40 p.m. What would be the train's velocity? Its velocity could come down. For example, it starts start to decelerate and stop at a station, its velocity could come down like this, and it could be 0 after a certain time, means it has come down and stopped at a station. So, this could be the graph. So, now what is exactly the velocity at a given time t? So, if a distance s is usually written as a function of time. So, if you do not mind, x t is the standard way physicists write. So, I will just put it in a mathematical way. S is function of t, s is the distance and f t is the function by which it is related with the time. Is the train speeding with the distance or it is slowing with the distance, everything can be captured. So, you can so time, so at every time we see the nature of the motion of the object. Now, if I say exactly what is the speed at this time, you might say, oh come on, it is so difficult to find exactly what, how, because an instant of time merely passes. Suddenly you are in the past and suddenly you are in the future, you hardly understand what an instant is. But this notion of instantaneous velocity has severe and important ramifications in physics and also for mathematics. So, how does one do it? One says, okay, let me see what happens if I see if after a very small amount of time, say delta t, just delta is to talk about very small time. So, what is my, so I have a, so s dash, I come to s, I was at time t, I was at s, at time s dash, at the time t plus delta t, at a very small time I am at s dash. So, this is my distance. So, assuming that over that period I have moved in a given direction, that is I have not changed my directions much. So, for a very small instant of time, so we can compute the average speed over that distance, which would be f of so this thing is also written by the physicists as a change in the distance, very small change though. So, you can make the change on the, for example, at this point you want it, say at the point t you want it, but you can make the change either here t plus delta t, t could be positive or it could be t minus delta t, whichever way you want. You can look at what was the velocity. So, you are looking at the velocity, you are looking at the distance it had covered just few seconds before, or just you are looking at the distance it has covered few seconds after. You can do either. Of course, you can say this, though instantaneous velocity is a very strange thing to think about, but at time 340 it did, the train did have a velocity, right. Then the question is, if I know the velocity of this, or the time that the distance that it has covered in this small time period, and then if I make the time period much smaller and smaller and smaller, so small that the time period goes towards 0, then possibly what I have at the end is the instantaneous velocity. So, this brought in the concept of, now this whole thing is a function of t, because ultimately everything is depending on the choice of t, the delta t. So, if I fix the t, then it is the choice of delta t can be now changed. I am making the intervals around the point t smaller and smaller. If you want to be more comfortable, you can put instead of t, t0. So, this is delta s by delta t, which is a function of t. So, delta s is a function of delta t. The change in velocity, the change in distance is a function of the change in time. Now, I want to know what would happen to this change, this rate of change or this velocity. So, how much has the velocity changed? So, what I am measuring here is the distance covered by the time. So, average velocity over this small interval of time period, the small time period. So, I want to know if this small time period be made as small as I like, I can make it as small as I like. Basically, I want to in my mind shrink it and bring it to the point t. Will this ratio move to anywhere? So, taking this process was understood and called by Newton the notion of a limit. So, as I am making the time go towards 0, the change in time go towards 0, this average velocity over this very small time period is going to what is known as the instantaneous velocity v at the time t. It is sometimes also written by this fashionable symbol called ddt of s, which is called the derivative of the function s with respect to the time t, computed at the time t. If you are slightly confusing, you can put this as t naught if you want. So, I am exactly looking at the time t naught. So, then you can write this at time t equal to t naught, that is it. So, this is nothing. So, when Lord Kelvin, whose name you must have known for the notion of absolute 0 minus 273 degrees Celsius, was taking a class in Cambridge and people were getting rather fussed about this notion of derivative. He was taking a calculus class. He simply told, do not get so much worried about it, this is nothing but the velocity. So, here the first idea of this intuitive idea of the limit comes from trying to understand the motion of a body. Now, this was just one category of function where we are looking at distance moved by a body as a function of the time elapsed. Now, as a mathematician, we take the question further. Now, the mathematicians would say all this work by Newton was largely for physics, for motion of bodies. It was Leibniz who got into asking more general question, and later on Euler who took it up in much more detail, is that when I have a general function y equal to fx and when x move towards a real number a, of course f is a function on a real number line, when f is just a function say from R to R or from some interval a b to R, does not matter, you can, that is your choice. Now, when x goes to a, where does y go? That is the question. Now, the interesting part of this whole issue is that first of all, what is the meaning of x going to a? The whole question is what is the meaning of x going to a? See, we are here in this course not to show you very basic how calculation of limits or doing very simple calculations and showing you what is done in a class. This is a course for the ambitious people who I have mentioned in my introduction, and hence we are essentially looking at concepts at the first place. So, concepts are of central importance in this course rather than just showing you examples by which you can pass exams, because somewhere the subject must come first and other things has to take a back seat. So, where does y go? Now, you might ask me what is the meaning of x going to a, or what is the meaning of delta t going to 0, and when I was in my 11th standard, this was the equation our teacher wrote on the board, and we were quite finding it pretty strange because we hardly understood, we had no knowledge of the calculus. So, we asked our physics teacher, what do you mean by this, what is meaning of delta t goes to 0? He says, oh, the delta t tends to 0 in the limit. We asked him what is the meaning of limit. This is a story I tell to many of my students. He said, you see, limit means coming but still not coming, which might appear that is a piece of joke, but it's somewhere it is essentially the true fact. So, what does x goes to a mean? So, here on the number line is your real number a. What is the meaning of x going to a? Now, x can approach A from either side, from both side, either from the right or from the left. So, x can come approach A from this side, x can approach A from this side, but x need not be exactly equal to A, need not jump onto A. So, here, so if x comes from this, so we say x goes to A from the left side, A minus, and x goes to A from the right side, A plus. So, this is called the right hand approach and the left hand approach. So, when I am meaning x going to A, I am trying to mean that I can take the variable x variable move from any of the sides. Now, what do I mean by that, where does y go? I want to mean by where does y go is that if I make x approach from either this side or that side, what is the value of y? Well, what is the value of y? Where is the value of y going? We say that the y value goes, if y value goes to a particular value L. So, if y goes to L or the function value goes to L, that is goes to L, when x goes to A, means it does not matter whether x is moving to A from right side or left side, the fx value goes to L. Then only we will say, in that case we will only say that L is the limit of the function, limit of the function as x goes to A. So, what it means by fx going to L? It tells you that fx is somewhere near L, the fx value, that fx value could be on the right side of L and could be on the left side of L. See, x need not be A because the function itself need not be defined at A. So, here is my, maybe not defined at A, and it is like this. So, function. So, now, so this is suppose this is your L. Those who know some calculus, you might understand what I am trying to do. But suppose this is the L that you say that it approaches. So, what it means? So, whenever I find an x such that fx is very near L, either this side or that side, I should be able to tell you a corresponding x near A. That if I say x is near L, fx is near L, you have to show that x is also near A. Then only it means that fx is going to L when x is going to A. Whenever, I repeat it again, which is very crucial, that whenever x is going, if you take fx value very near L, you have to tell me whether the x that you have chosen of that for that fx is actually near L, actually near A. You cannot say fx is very near L and x is somewhere very far from A, then this whole thing does not stand a chance. This little fact that if you claim that you have a fx value near L, you have to also show that that corresponding x must be also near A. That is exactly the meaning that fx would be near L whenever x is near A. So, or rather whenever x is near A, fx must be near L. So, if you tell me fx, if you give me an fx near L, you should be able to show me that x is near A. If x is far from A, does not matter, right. For example, I will tell you, give you an example of a function like this. So, let me define the function. Fx is equal to 1 when x is negative, is equal to 2 when x is positive. So, when it is 1 is negative and it is 2 when it is positive. Now, here the function is taking either 2 or 1. So, whatever x will take, either it will take 2 or 1. Now, if you claim that f x takes the limit as 1, okay. Now, suppose I take a x here, a y here, a functional value. So, suppose I say that in this case the limit of f x as x tends to 0. So, now suppose I claim here in this case that limit of f x as x tends to 0 is actually 1. Sorry, yeah. So, suppose now here is a point I have chosen here. So, here is my 1. So, I have taken some length of very small length, say 1 plus 1/10, and this is 2 by 10. So, this is 1 plus 1 by 10th and 1 minus 1 by 10th. So, this is my interval that I have taken. Within that interval, that open interval 1 plus 1 by 10 and 1 minus 1 by 10, I take any point. So, I have to show that the corresponding x here, the corresponding x here in this particular case. So, given this x, this value, is there any corresponding x for which if x is near 0 and it gives you the same value? There is no corresponding x, because the function takes only the value 1. So, okay, order 2. So, you might say okay fine. So, this is a very stupid thing to do, to take a value near 1, because the function does not take the value 1. Okay. Then what should have, so what are the values it is taking? 2. So, I can now only consider the function value either 1 or 2. So, 2 is it can it be considered around, so it is within say this particular neighborhood of 1, right. Now, in this neighborhood the functional values could be just 1 or 2. Now, 1 does not corresponding to any x on this side, but if you shrink the neighborhood, then obviously you can't get any functional values. So, what it appears is the following, is that in this very special looking case where you have only 2 choices, and when you approach from the left you come towards 1 and you approach from the right you can come towards another, you cannot talk about a limit, you cannot show me up, you cannot just keep on shrinking the neighborhood and every time you get the interval, every time you take a point in the interval there will be a corresponding point in a corresponding small interval around x, you cannot do that. So, unless you do that, you cannot show the limit exists. That is your high school knowledge of having the left limit equal to right limit, means that any interval around the chosen limit, if you take any point in a whatever be your interval size, any point that you choose in that interval must have an function x value, must have come from an f x value which is in a corresponding small interval around the point say A. So, which means that if you give me any interval around the limit L, I should be able to tell you an interval around the point A. So, this can be explained by a very simple example. Okay. I will use the book of Spivak where some very fascinating examples are in place. Now, for example, I take the function y is equal to 3 of x, and let us look at x, what happens when x goes to 5. You would say, oh, it does not matter, it is just 15, I know it, but no, I am not talking about just doing and getting the answer, I am talking here about the structure that will tell you that what you have done actually is making sense. see, this will bring us to something called the epsilon delta argument, and people will put up their hand and say, oh, I do not like it, it is so horrible. But please understand, this is just nothing but a translation of your English language into symbols. So, that is exactly what the epsilon delta thing does. So, now I said okay, he said, I said okay, so let us do an experiment. So, I give you an interval say of length 1 by 10, that is, you say okay 15 is the limit, I agree, okay, I will test, your 15 is your L. So, I will take 15, so here is y is 3x, y equal to 3x, and so here say it is 5 and this is say 15 somewhere here at 5. So, here is 15, maybe my drawing is very bad. So, now let me take an interval of length 2 by 10 totally. So, it is 15 plus 1 by 10 and 15 minus 1 by 10. Okay. And now, once we have done this, so what have we done? We have done the following. So, I am telling okay. So, you say that your limit L, right, is such that you take any point here, any point, let me take any point y. So, I take a point y equal to 3x such that 3x value is lying between 15 plus 1 by 10 and maybe I should rub the board and do it better, 15 minus 1 by 10. So, now I am just getting a value. So, for me I made a small interval, it could be lesser, it could be bigger also, but lesser is what is required. You always understand this is whole story comes from this instantaneous velocity business. So, you have to shrink the intervals. So, I will take a function for a, so take a functional value 3x for some x where it is lying between 15 plus 1 by 10 and 15 minus 1 by 10. So, subtracting 15 from both sides, I have 1 by 10 x minus 5 x minus 15. I am subtracting 15 from all the sides. Okay. Now, what sorry 3x minus 15. So, what I will now do, I will divide all the sides by 3. It can be done because we are doing division by a positive number. So, what do I get? I get minus 1 by 10 less than x minus 5 less than 1 by 10. Sorry, I had divided by 3. So, I have to have 1 by 30 here, sorry for the mistake. Now, what does this mean? So, x must now lie. So, x, where should x lie? So, x should lie in the following interval. So, this whole thing can also be written as x minus 5 is strictly lying by 30. If you look at this argument very carefully, you replace your 10 by any epsilon that you want. Epsilon, why I am talking about epsilon? Because it is a standard in mathematics. And who has made it standard in mathematics? A very famous French mathematician called Cauchy. So, all these definitions that you see here was brought in by Cauchy well into the late 18th century. So, it is Cauchy's book which gave modern calculus this flavor. So, I am been able to talk about the structure. So, any x which is lying within this zone 1 plus 30 from 5 either from this side or that side would give me this. So, if you give me a functional value which is this close to the limit, I will give you an x which is that this close to a x, I will give you, I will show that the corresponding x's must lie within this particular band around this point A. Your 5 is your A, x tending to 5, so x is your A. So, what does it mean? Of course, I am not taking x equal to 5. Now, what does it mean? So, give me any epsilon, I will give you some other number delta. So, here if my epsilon was 1 by 10, my delta is actually 1/3 of epsilon. So, you can just replace it this with epsilon, because anyway you will divide by 3 and you will simply get this answer 5 minus 1/3 epsilon, 5 plus 1/3 epsilon. So, from mathematical point of view, what is now the meaning of a limit? So, with this definition we will end the discussion and we will give one more example how to show, for a very curious kind of example, to show that two examples that how to really find out this epsilon delta, and an example in the next class showing that why in what situations even by this epsilon delta argument you can show that limits do not exist, right. So, these are the conceptual framework that we have to really get into our mind. So, do not get too much pissed off by this epsilon delta thing that I am going to write now, you might just forget it, but you just have to remember this fact. If fx is very near y, is x very near a? That is the question. If you can show it every time, then you have actually showed that fx goes to L when x goes to a. So, if fx is very near L, is x very near a? That is what you have to show. So, this epsilon delta are quantification of these words, nothing else. So, when I am writing this statement, a statement which many of you must be knowing very well, a statement like this, it means given any epsilon greater than 0, no matter how small, does not matter, there exists, so the meaning is this, there exists delta greater than 0 such that whenever 0 is strictly greater than x minus a modulus less than delta, means whenever x is in the neighborhood of a plus delta and a minus delta with x not equal to a, that is why we have kept this symbol, we have the difference between fx minus L to be less than epsilon. So, whenever x is near a, fx is near L. So, whatever be the nearness you want of fx from L, I will give you a corresponding nearness. You might say, oh, it looks very funny, because you sometimes say, okay, whenever fx is near L, show me that x is near a, but why can't I think about the reverse thing, that I tell you, okay, x is very near a, I tell you x is, I give you x very near a, okay, but show that fx is near L, in what bound fx should be, to how much. This is a very tricky question, because sometimes what would happen is that for some intervals, some small intervals, you might show this, that there is a corresponding one, but for some other intervals you might not be, if you make it smaller, you might not be able to show, the function could be that bad. So, that is why it is always important to say that I already know that fx is, I am choosing fx from the intervals very near L. If I know that x is very near a, my job is much more clear, rather than looking into the reverse direction, that if I give us x near a, is fx near L. Of course, in most cases that would be true, but in some cases things might be slightly not so easy to get to. That is why the reverse thing, that what would happen is not easy to guess. Now, one interesting thing is that another reason why this approach is much more useful, because if you give me the epsilon, the neighborhood in which you want fx to lie, then from that I can tell you which x should correspond to this fx, whether that x is actually in a neighborhood, small neighborhood around A. So, this calculation is actually much more simpler. That is why we try to define limit. Now, it has now become a definition that whenever you tell me the distance I want fx to be from L, I should, corresponding to this epsilon, there must be a delta such that every x for which fx value, f takes this value fx, must be in that neighborhood, the delta neighborhood. Okay. That is the simple idea. So, again I am repeating and ending this lecture that whenever x is near A, we should have fx near L. That is the standard way of looking at it, because it says limit x tends to A when fx is equal to L. But a more structural way of looking at it is that first ascertain, for example, you can have functions like this, right. I am just telling you. Here there is a small break here. See, you take this neighborhood around say 0, and take any one of them as the limit, this value or this value, there is a small gap between them, and take a small, say I say that okay, corresponding to this. So, okay, what are the fx's? So, fx's are all in, these are the fx's corresponding to this, right. So, the fx's, all the fx values are within this zone, right, this particular zone, right. So, fx value is within that. So, here if I magnify it, here there is a small gap here, and from the x that the interval that is chosen around x, if I say this is the limit, it shows that fx values are within this. So, I can always, it shows here, or maybe if we choose a limit like this, I can still shrink the interval, and okay, you might just find the limit values are here. Then any fx value that you have here, right. So, whatever value that you have here in this place, I can choose a very small, whatever fx value so what is happening, that here I have made this small interval, and corresponding to which these x values are coming from this small interval. So, I have some values around a small interval of x, and immediately I can have the fx values lying within this interval, but this function does not have a limit. You see, it does not have a limit, because ultimately they would give me two different values if I come from both sides, if you look at it in the traditional sense. So, even if I look at it in the traditional sense, going from a distance around A to a distance around L is not the correct idea. The correct idea is to come from the distance around L. So, once I am sure that fx is lying within that neighborhood, for whatever be the neighborhood, however small. So, for example, if my neighborhood contained this, any point here, then for these zeros here, you see what is happening. For these x's here, the function for this particular x's here, for example, very small neighborhood, for very particular x's here, very small neighborhood, there are functional values at this point, right, because suppose this function is increasing, suppose like this. So, for very small, if the neighborhood is very small, at the upper part there are no functional values. So, you might be tricked by the fact that because in this part there is no functional value corresponding to this part, corresponding to x equal to 0, this part the values are all here. So, in this part there is no x for which, so you are telling whatever fx I am having here, they are actually corresponding to x's here. So, you have given me a small x around, I am showing okay they are around a small neighborhood of fx, but that is not true, because in this part there is no functional value. I have to pick up a point anywhere in this neighborhood. So, I have to take the limit point and I can take any point in that neighborhood. Other than L, if I take any other point, there must be a corresponding x which is near A, that is the meaning of limit. Here it is a very bad trick, the function does not really have a limit, but I am taking a situation where I know that this upper part does not have any functional values. It does not correspond to any point here, does not corresponding to any x here. But I say okay, all the values here is for these fx that I have taken, x's that I have taken, all the values of fx are here, come from here. So, because you have already given a very, you have chosen your neighborhood around x in such a way that you get a small neighborhood around fx, where fx values, a part of the on the top does not have, this part does not have any x, then there is no functional values here, there is no x for which any point here is a functional value, but here everything is a functional value within that small neighborhood. This part, these are the functional values. So, what we will say, okay, I have taken such a small neighborhood, so I am getting a small neighborhood for whatever, all the functional values are lying within that small neighborhood from here. So, I have taken any functional values that I am getting on that neighborhood is actually corresponding to some x in that neighborhood, means you have actually here done the reverse thing, you have taken some neighborhood very near x and you are showing that now I am taking only those x's for which these are corresponding to values of fx from here are in that neighborhood. So, I have x values which are in that neighborhood, so I can forget about the rest. So, this is a very tricky thing and this has to come into your mind that this is not the correct approach to go from the x thing to the fx thing, you have to always come from the fx thing to the x thing, that what it does not matter whatever be the interval, any point that I choose it must correspond to an fx. This may not happen in this sort of situation when limits do not exist. You may have an interval around fx where a point does not correspond to a given interval you have already chosen around x. So, you cannot choose an interval around x a priori, you have to choose around fx and you have to make sure whatever be your point you choose in that interval must correspond to an f of x. The y must be f of x, where x is in some neighborhood which is near, which is a small neighborhood around that point, around the point. So, this is something extremely important which is hardly taken care of. So, we will give some more discussions in the next lecture. Thank you.